Thanks, Richard. So what we've done at Cerebras is take Moore's law to the extreme. We did that by building the largest chip ever made, and it provides cluster level computing in a single chip. So this is the Wafer Scale Engine 2, or the WSE2, as we call it. It's currently generally available and being used by our customers every day. It's over 46,000 square millimeters in size, 2.6 trillion transistors on a single chip, fitting 850,000 cores. And with all of these cores integrated on a single piece of silicon, we get some truly mind-boggling numbers for memory and fabric performance, as you can see, because everything's on chip. So let's go to the next slide, Richard. Thank you. So building the WSE2 was obviously the first step for us. But we also needed to go and solve packaging, power, cooling, and co-design a hardware-software solution to build a high-performance system that could fully utilize the potential of the WSE2. And for that, we built the CS2 system, which is shown here in the bottom of these racks. They fit into standard data center racks. They can be air-cooled or water-cooled using standards-based connections. They're easy to deploy, operate, and maintain. And using these individual CS2s is basically just the beginning. It's a foundational building block of our solution. And thank you, Richard, on the next one. Oops, here we go. So our full solution, of which the CS2 is a critical component, is called the Cerebras Wafer Scale Cluster. And the Wafer Scale Cluster is a collection of purpose-built hardware and software that enables effortless scaling from 1 to 2 to 4 to N being hundreds of CS2s. And so this image is just a sample of what we can build and the scale that we can reach. We'll talk about that a little more later in the presentation. But before we get into that level of detail, let's discuss what's in the wafer scale cluster. So the wafer scale cluster is a high performance and scalable AI appliance. It's deployed as a full hardware and software solution that can scale to hundreds of CS2s. And to take advantage of this hardware, all a user needs to do is log in, use a simple Python interface to launch jobs and specify how many CS2s to use for that job. The cluster is automatically going to handle the distribution of the workload without any overhead to the user. And so the major components of the wafer scale cluster include the memory X layer. Now this layer contains the weights of the network, as well as the compute to perform the optimizer updates. The Swarm X layer, which is specialized networking hardware designed to ensure high performance within the cluster and move weights and gradients from many CS2s back to the memory X servers. Input pre-processing nodes, those run the data loader and feed the CS2 with data fast enough to ensure that the compute is saturated on the CS2. And so all of these building blocks make up the wafer scale cluster appliance. And it operates in a mode that we call weight streaming, which I'd like to talk a little bit more about in the next slide. Thanks, Richard. So to address the traditional challenges of scaling, we've created a new execution model that we call weight streaming. And we take what's traditionally been a complex and intertwined problem of distributing memory, compute, communication, and synchronizing it all together at the same time, but instead we've separated those problems. So we separate the memory from the compute, fundamentally disaggregating them. and it makes the communication more elegant, more straightforward. So the reason that we can do this is because neural networks use memory differently for different components of the model computation. So we can design a purpose-built solution for each type of memory and each type of compute that the network needs, and as a result, untangle them and simplify the scaling problem. And by disaggregation, the weight streaming execution model provides unique flexibility to users by allowing for independent scaling of model size. So let's go to the next slide, please, Richard. So in this execution mode, all of the model weights are stored externally in the MemoryX unit, and they're streamed onto the CS2 system as needed to compute each layer of the network, one layer at a time. So the weights are not stored on the CS2, not even temporarily. And as the weights stream through, the CS2 performs the computation, and the resulting activations stay resident on the CS2, ready for the next layer. So on the backward pass, the gradients are streamed in the reverse direction, back to the MemoryX unit. And there, the weight update is performed in time to be used with the next iteration of training. So now I also want to talk about how we handle scale out. So if we look at existing scale out techniques, the most common and simple form is data parallel. But it doesn't work well for large models because the entire model needs to fit in each device. So to solve that problem, the common approach is to run model parallel by splitting the model, running different layers on different devices as a pipeline. But as you use more devices, the activation memory increases quite significantly to keep that pipeline full. And so to avoid that, it's common to run another form of model parallel by splitting the layers across multiple devices. But this has significant communication overhead, and it becomes quite complicated to split these individual layers across devices. So because of all these constraints, there's not a single one-size-fits-all way to scale out today. And in fact, in many cases, training huge models requires a hybrid approach with both data parallel and model parallel being utilized. But with our architecture, we've drastically simplified this process to scale out to many CS2s using only data parallel scaling via the SwarmX layer of our appliance. And so SwarmX is our specially designed interconnect for data parallel scale out. It sits between the MemoryX unit that holds the weights and the CS2 systems for compute, but it's independent from both. So SwarmX broadcasts weights to all CS2s and reduces gradients from all CS2s. So it is a bit more than just an interconnect. It's an active component in the training process, but purpose-built for data parallel scale out. And because it's modular and disaggregated, you can essentially scale out to any number of CS2 systems with exactly the same execution model as a single system. Scaling to more compute is as simple as adding more nodes to the SwarmX topology and adding more CS2 systems. So let's take a quick look at some of the larger systems that we've built so far using these components. So last year during supercomputing, we unveiled the Andromeda AI supercomputer, which is essentially an exaflop capable AI supercomputer with the ability to support 200 billion parameter models or even more. And this is built from 16 nodes of wafer scale clusters that we just discussed in the previous slides. So basically 16 CS2s. And this system, or this cluster, I should say, is in use by our customers daily in a cloud environment that we maintain. And now I'd like to talk a bit more about what's available at Argonne. So at Argonne, we have a 2-node wafer scale cluster available, which supports 2 CS2 accelerators. And this supports up to 30 billion parameter models for both NLP and CV workloads, and can be used to distribute jobs across one or both CS2s, pending the preference of the user. And so before we go to the software and programming aspect that Richard's going to speak through a bit more, I wanted to leave you with some takeaways on our hardware. So in summary, our hardware, our systems, our clusters are quite differentiated from other AI accelerators in market. Again, we've built the largest chip on the planet to accelerate AI applications. This chip has 850,000 small cores with a large proportion of on-chip SRAM near the compute in each core. We've built the machine with the ability to accelerate both unstructured and structured sparse neural networks. We've built a novel technology to disaggregate compute from memory, allowing for larger models, to be supported on single to many accelerators. And we've simplified the scaling methodologies, especially for scale out. Now, before handing it over to Richard, who again is going to speak more about software and programming, I would like to invite the audience to please go check out the Hot Chips 34 website. Last year, our co-founder and chief hardware architect did a full deep dive on the chip, the system, the cluster. The slides and the video recording are available there. It's extremely informative, worth a view or 2 or 3, depending how excited you get about this type of information. So I'd welcome you to please go take a look at that.